I promised that we would. And today we will basically try to go through the, at least I'll try to go through exercise 1, sort of the, make sure if I, try to see if I can match the sort of the given answer, right? From, at least from an intuition perspective, of what I kind of assumed the solution would be, or the starting point would be, and see if that matches in any way. Because I now things became clear when I just like in the last stream realized that this is not the wave function. This is just this isn't a function, right? It's just the usage of psi confused me. The wave function is this, right? And so the wave function in our assumptions, which is also what they then do in the exercises, the actual wave function, you know, the actual wave function of x and t is something that we can then assume kind of has this form of like this, right? So e to the, like, I'll wrap that up into a constant, into a variable, right? Times this. Exactly. And especially, so let's start with b, right? So we say, so here we assume this is the wave function, okay? So, and now we want to see that the probability density is independent of time. No, that was, sorry, c. So we got to assume that they overlap partially. And we start with this function, right? And so, that's what they, okay, so yeah, and then they do this whole thing with a square here, and that's what they get, right? And that's where I want to get to, yeah. Because it says then that where we have that psi 1, 2, periodic function, I'm not so sure actually. That'll be the beginning, right? No, sorry, that's the starting point. Then after time t, there's obviously that component to it, right? So this is just the wave function at time 0. And so, but here we kind of have, like, I'd go ahead and assume these, right? So this is what's time dependent, and this is what I just keep forgetting, and it's this minus I times this energy, which is sort of, you know, the overall energy times t. And this is taken from the I think Schrödinger equation, right? So Schrödinger equation, and then also we want to take as a reference wave function, free particle or something like that. Is it free? I don't know if it's free particle, but that would be that's sort of an assumption to make, right? Equation in English, exactly. And so IET divided by h bar. So minus IET divided by h bar, and then we have all that, you know, half of psi 1 of x plus psi 2 of x, okay? And so we want to calculate the density function, so that's kind of this thing here squared, right? And then it's basically, you know, the way these looks like, and again, maybe it's like I do that, like it I hate because I hate it because at some point you just have to make a bit of a switch to not get stuck and just kind of follow the formulas, right? Without like I keep struggling with, you know, the intuition behind why is these the sort of the transpose times the sort of itself, right? Okay, because it's a generalization when we're thinking about complex valued wave functions, because in the real case this is just these times itself, right? I guess maybe one could think about, like, if you think about complex numbers, right, as being, and you see I'm already going on a tangent, but if you think about complex numbers as like, you know, vectors in a two-dimensional space, right? Because that's the idea, right? So it's like I squared is -1, right? This means if you do I twice, you go to -1, right? So because I think that's the idea, right? And that's kind of like I is a 90 degrees rotation. So if you think about complex numbers being rotations in that space, then you can think of these being like the multiplication being a concatenation of rotations, right? And so based on this definition, if you think about, like, yeah, well, but then why would that make sense? So if I say I square, and it's the, okay, it's the absolute value, because you want to take the absolute value. I think that's the trick. It's not that the squaring is like this, it's that the fact that you want to take the absolute value, right? Because the sort of the in that plane, if this is let's say I, right, the conjugate is this, is minus I. And so if you imagine, like, so well, if you want to take like the absolute value of I squared, right, how would you do that? Well, it's kind of like, it actually makes sense, right? Because that's how you would do it. You would apply the operation once, because you're going to get -1, but you're going to get +1 because you want to get the absolute value. So a trick to do that is you apply I once, rotate 90 degrees, and then you would apply sort of the of course the conjugate operation. So like you would rotate again back to 1, and that's how you do this, because you're exploiting in a way symmetry here. But that's also not, I'm not so sure that's, like, I'm happy with the, no, I'm not so sure that applies though. That's it. Because if you take a more general rotation and you say more, maybe you want to do these, like, you know, like 4 degrees, the absolute value of that would be 0, right? Because of that square, you do a square, and then the conjugate of these is the sort of the opposite rotation. I don't know, that's something to explore. It just why is that? But that's something definitely to explore. There's got to be some intuition there, but let's just follow the formula just for the sake of not getting stuck here, right? So you get that. So now again, the conjugate is just the change the sign of the complex of the complex things, right? Of the complex components. And so I mean, essentially it's these things square, right? So you would basically, I can just try to do, so you know, that's something that goes all together with this constant here. And so, you know, you kind of have, E derived minus, you know, let's, I don't want to write the whole thing here, right? So I'm just gonna like, this is something that is, you know, so this is like that, and then it's I don't know, let's call it P. That's bad because it's not momentum or anything, but it's so let's assume, and this has got the time in there, and this is like the time and the energy, and you know, let's just define it like these, and just to make the writing easier. Psi 1 x, right? So because you're multiplying these twice, right? So it's basically no, not twice, but like the so you've got the complex thing here, and then you would get the normal, right? And so of course this is you know, squared, right? So this seems like 2 here, because you're doing like you know, a time, like a squared plus b squared, like, I mean, you can't apply the formula directly, but like you're doing the whole thing with the computation, not computation, like the distribution, right? So these, so then you'd get like also the same constant here. I'll you know, this E thing here. Again, it's a plus, right? It's a plus because we're changing this. And so now you get basically psi 1x conjugate, complex conjugate times psi 2x. And then you get another term, which is the 2p2, and then you get the psi 2 conjugate times psi 1, and then you get a similar term here, which is basically the psi 2 conjugate times 2. And I mean, again, like you can then say, and I'm going to cheat here because I'm going to take a look at the solution to see what we're trying to arrive, right? Because we're trying to arrive at this expression here. And so because now we know that they overlap, so we can't just cancel terms, because I think that's what we're doing in the other in the other points, where we're saying, well, if they don't overlap, then it means that this product is 0, so we can cancel these terms. Oh yeah, and by the way, actually these go like these actually disappear. Sorry for that. Those things disappear because they multiply in the conjugate as a minus, and then they multiply with a plus. So these actually things here disappear. Like the not these, but like the, so the, I don't know actually if the whole thing disappears or not. And, no, I think this can stay there. Yeah, so that definitely disappears. Right. They disappear because in the conjugate form you'll have like a plus I, and the non-conjugate form you'll have a minus I, right? And again, it's the same energy value. Here they don't cancel because, so let's put it this way. So this is E1. So remember, there's E1 and E2, right? So there's these two different energies, because this eigen, like the energy eigenvalues are then attached to these. I don't know why I'm doing it like that, but it just feels like that's the way. To be honest, I really don't know why, but I say that's the reason why these don't cancel, because I think in this case, then what you're getting here is you're getting like, this is wrong. So in here, you're going to get something like E. And so originally you have minus I E1 H bar, right? And then you're gonna have I minus, so E minus like the power of minus I E2t, right? So if you just kind of develop that into just one exponent, would be like minus, like you know 2I whatever, and then there's just this kind of like I E1 minus E2 thing here multiplied by the t, because these are two separate energies. That's why you can't cancel these terms here. Sorry if that's not clear. And so, and this is where then they define, something like this later here, I guess. h bar w. I don't know why, but like that's to simplify things. But that's the coefficients here would stay like that. So bear with me. So here you don't have coefficients. So you actually can take these two pieces, right, and say, well, this is just the respective like absolute value squared of these eigen functions. So you can that gives us the first part, right? The square of like psi 1x, the sort of the absolute value squared plus the absolute value of psi 2 squared. That gives us the first part. So I think we're on the right track. That gives us this part here. Now we need to develop this part here. Okay, so how do we do that? I mean, you know, that is essentially, I don't know if one could do that, right? But that is essentially, doesn't matter which one you're conjugating. Or does it? Because then they go and say it's the absolute value, yeah. Huh. How would they? So I don't. What are they doing? They're doing a. So they're redefining here. We have set psi 1 to. Here I think here what they've done is they've this is so. Okay, but that's actually kind of what I have done, isn't it? Like I think that is the definition of what I've been trying to do here with the p and whatever they called it, just like psi of x, or whatever that symbol is. But then I don't know how would you compact that term into, like, that is obviously the same term. This exponential is the same term, right? So the half goes away because you would kind of have like 2 times e, you know, to this thing up here, right? And so let me think. Divided by 2, so the 2's go. So you have I. And I think then that's what you can have, right? Looking at the solution, I think that's what you're doing here. You're basically taking that. So you're saying, so you're taking these and saying, look, psi or whatever this symbol is of x equals minus the energy 1 t h bar. So that's 1, and then the 2 is the same, but for E2, right? And so essentially, yeah. So essentially, you end up with this expression because that's what you're doing. You end up with this expression. So just forget about these. Because you have This is really it's a pretty convoluted way to describe that. I think they mean they do it for both. You know what I mean? Like psi 1 comma 2. I don't think that makes sense. I mean, there's no h bar w. I don't know where to take the W from though. Energy. Okay, energy equals h bar W. So that's what they do. That's how they do these. Anyways, the way they arrived at probably with the cosine is by replacing the exponential because basically what this does is they so the complex exponential sinus cosine complex exponential sinus cosine no. So sorry guys, back in a second. Cool. So how will I get there? So basically, there's the Euler's formula. It's not Euler's formula, but like cosine plus I sine exactly. That's the thing, right? So yeah, that's I think how I get the cosine in there. So the thing is, how do you get rid of the sinus though? So I'd assume the one way to do these, maybe I'll just get rid of that here, and I don't really, I'm sorry, I'm not really keeping track of these things. I just do this for myself and they stay in the video, so I'm not really going to archive this anywhere because I really don't know where that would make sense, and I just don't want to keep that. So you know, so e to the power of I whatever thing it is here, let's assume so this is basically cosine of this thing, right? Plus I times the sinus of this thing, plus or minus, I don't know. Sorry. Right, so how does this sinus go away? Because that is basically these, yeah, sure, then you have this energy stuff in here. How does the sinus go away? So these things are eigenfunctions, right? And then there is a non-zero overlap. But like, what is that non-zero overlap? Maybe, okay, maybe, yeah. Maybe I'm wrong. So maybe it's essentially the conjugate of these times these and the conjugate of the other one times the other. So like, I think that is maybe what they mean by these, right? This is some, this I don't fully get how they get that, because that would make sense. Then it would make sense. So this is where I am. So I have forget about the exponent. I'm just trying to understand, like, I'm trying to understand how, like, what to do with these and what to do with these, sort of with these two things, right? And it actually, it might have to do with the notion of, you know, maybe for some reason this equals these, you know what I mean? Like, these times that. That's kind of, this is what's not clear. Like, how would that be? Just, I'm not used to manipulating these kind of expressions, right? So, but maybe how could we test that, right? So we have, let's just think in terms of numbers, complex numbers, like a and b, right? And then they're complex conjugates, a star times b, a star b star, right? So, you know, maybe a times b star, that's my hypothesis, plus a star times b equals, like, that is my, you know, that's my current hypothesis. A times b, that's my current hypothesis. How do I know whether that's true? Complex number multiplication identities. Maybe I can find some here. Maybe there's some cheat sheets somewhere. Look at these. Maybe we can use these. So yeah, maybe we can use these, right? Because a plus bi times maybe let's try to use that. Let's try actually do that by hand. This means we'll need some more space in here. So let's define a number a. I'll just say x plus yi, and so a star is basically x minus yi, and then b is like p plus qi, and b star is p minus qi. And so if I want to do a times b star, then this is like x plus yi times p minus qi, right? And then I want to do plus plus a star, so x minus yi times b p plus qi. And now let's do the multiplications here, and then we have x p minus x qi plus I pi, and then we have plus x p plus x qi, so these guys will cancel, minus y sorry, I'm doing something wrong here. Let's start again. I'm missing the I squareds and stuff like that. That is dangerous. So we're doing x times p minus x qi, right? And then we're doing plus p yi, and then we're doing minus y q, or and then it's I squared, so it's plus iq. That's the first term. And now the second term is xp plus xqi, so these guys will cancel out, and then we have minus ypi, and so these guys will cancel out, and then we have basically the same plus iq, right? So essentially we have 2 times xp plus 2 times yq, right? And if we cool, if we so that's kind of the result. And then does this equal this part? I guess so, right? Because again, or I mean, let's try, right? A times b. I mean, if it's the absolute value, it means that it's always, we're gonna get rid of all the minuses, right? So a times b would literally just be x plus yi times p plus qi, and I think the trick now is going to be this, like xp, right? Yeah, okay, the two goes out, and so I can get rid of these. So xp and then plus ypi plus x qi, right? Okay, so not exactly. Plus or minus yiq, but then again, this is all is an absolute value, so fuck, I don't know. xp xqi, no, sorry, that squared minus 1 It's the absolute value of each. So they're all positive. So but still you get that negative. YQ, XQI, YPI. So I don't know. I don't think that is trivial, but maybe that tells me something, which is that it's like so I've done basically this. If I now replace the it's XP plus YQ, XP plus YQ, X and P, and Y and Q, right? Yeah, but even like this, just there's actually no I in there, right? Oh, fuck! That is not like that's not the absolute value, right? That's the norm, right? Norm of a complex value. That's not the absolute value, man. That's the norm. The norm of the complex number. That's the problem. That's what I'm getting wrong. Yeah, look at this. And so it's a squared plus b squared. That's the norm. Yeah, so that makes sense. Is it? Does it? That's the norm. Let's try. Because I'm running out of time. So it's a squared times b squared. So I'd have to do you know, x plus yi squared, and then p plus qi squared, and you know, kind of that is, I think, the and that's what I have to prove. That's no times, you know, times. So that's what I have to, is the norm. That is just a norm. It's not the absolute value. It's the norm. I'm such a noob. The absolute value, for God's sake. What am I saying? So it's in this case it's 2 and then xp yq, right? So in this case I think it's going to be, since you have basically, I think I just don't have time, sorry guys, but I have to do, so it's like x times yi, and then because it's like, you know, x squared, or x squared, I don't have time. I actually have to. How long has this been running actually? How can I see the time here? 40 minutes. Okay, maybe I should, maybe just a little bit more. So x plus yi times x plus yi, and then I have x squared, and then I have like xyi, and I have minus yi, and I then have you know, y squared. Yeah, okay. So the oh, I'm just stupid. It's a squared. So no, okay. What am I saying? That's okay. So if this is the number, then a squared plus b squared is the norm. Okay, forget about these. So that's faster. So this means x squared plus y squared, right? Times p squared is q squared. That's what this is the product of the norm. And so then it's like x squared is p squared. Yeah, okay, x, but that's not okay, but that still doesn't tell me. That's definitely not this then. That's definitely, I don't think that's the case. Okay, so I'm stuck here. Because that would then say complex numbers. Product of norm. Maybe there's an identity somewhere. Yeah, maybe there's just a okay, so that's cool. Okay, so it's the square root of all this stuff. Maybe that's how it's done then. Or I mean, you can of course use the polar form to derive that maybe. Maybe not. Okay, we'll see. We'll see. It's not there, not there yet, but I think that is in a way the way to go. So this is one thing, and then I'll in the next session I'll try to do that, develop that again, and then also develop that. That's going to take a while, but I want to do that because it's going to help me. That's going to give me a bit more intuition, and it's going to help me mathematically for the future problems. I want to spend as much time as I can in this exercise. See you next time.